All right. So here we go. Hopefully you all wrote down some kind of a goal to go with this packet. Today we're starting 2.3, which is all about postulates and diagrams. So first off, what is a postulate? It's a rule that is accepted without proof. So in geometry, we have postulates that are kind of the building blocks of geometry. They're the rules that we're starting with in our system of geometry. That kind of define it and help us to make other connections and things like that. So we're going to go through 7 different postulates for points, lines, and planes. Some of them sound a lot like the definition of points, lines, and planes and stuff like that. Some of them don't. But anyways, so here we go. That color works well. This one does. All right. The first one is already kind of drawn there for us. The 2-point postulate. It's that through any 2 points, there exists exactly one line. So if you pick any 2 points, you can make a line with those 2 points, and that is the only line that you can make with those 2 points. And then, so in the other column, we have what would it mean if that postulate was not true? So if the 2-point postulate was not true, you could have 2 lines through 2 points or something like that. But we all know that, in our geometric system, lines don't curve, right? So in order for there to be more than one line through a set of points, you would have to curve them around. And that's not what lines look like in geometry, right? So keeping on kind of going through these postulates here, the next one is the line-point postulate. And it is that a line contains at least 2 points. So the picture is going to look very similar to this one, the 2-point postulate. The line-point postulate says that if you have a line, it has to have at least 2 points on it. So if we have line M, there must be at least 2 points on it. And in fact, lines contain infinitely many points, but there's our line-point postulate. If that were not true, well, if a line didn't contain at least 2 points, how many would it have? 1. And we don't have any lines with just 1 point on it. So what it would look like if it were not true is just a line with only 1 point.
Like a TIE fighter.
It does.
Kind of does. All right. Next, we've got the line intersection postulate, which is just a formalization of saying what we already know about what happens when 2 lines intersect. It says if 2 lines intersect, then their intersection is exactly 1 point. So a picture of what that looks like is if you have lines that are crossing, that are intersecting. Let's say we have line M and line L. Their intersection, the place where they cross, is 1 point. So that's kind of the picture that we're thinking there, and it's just a formalization of what we already know to be true about line intersections. If it were not true, then maybe their intersection would be 2 points. So like if you had a line L and it was trying to intersect with a line M, but in order for it to intersect twice, the line would have to curve around, which does not happen because lines are straight. So this would be 2 lines, so to speak, intersecting at 2 points. So 2 lines intersecting at 2 points. But then, when you have something like that in Euclidean geometry, lines don't intersect at 2 points. All right. The next one is the three-point postulate. Through any three non-collinear points, there exists exactly one plane. This is also kind of a formalization of something we already know to be true. When you name a plane, you use 3 points that are non-collinear. Remember, 3 points that you can make a triangle with. And so it's just kind of formalizing that with a postulate, saying that yes, through any 3 non-collinear points, there exists one plane. So if we had 3 points, A, B, and C, they can define plane P. Okay. Yeah.
Any 3 points that make a triangle,
right? Any 3 points that make a triangle, because that would make them non-collinear. It can't be 3 points that are all along a line together. Exactly. Now, drawing what would happen if the 3-point postulate wasn't true is a little bit difficult, but we're going to give it a go. So what we're going to draw, if the 3-point postulate wasn't true, if through any 3 non-collinear points there was maybe more than one plane, that's kind of what we're trying to draw here. So we'd have 2 planes through 3 points. So that would be like if we had point A, point B, and point C, and they define one plane, but they also somehow define another plane that's not the same as this plane, which is hard to draw, again, in 2-dimensional space. You would have to have some kind of a curvy plane that like comes up like a bump or something like that that can touch all 3 points. So again, really hard to draw and hard to conceptualize as well. So what we do need to know, though, is that mainly this. Through any 3 non-collinear points, there is exactly one plane and no more than one plane. Okay. So do your best with the drawing there. But anyway. It helps if you remember that planes are flat and not like bumpy or anything like that in Euclidean geometry. Okay. The next one, the plane point postulate. A plane contains at least 3 non-collinear points. So if you have a plane, we'll call it plane P, there must be at least 3 non-collinear points within that plane. And we know there are infinitely many points within a plane, but it's kind of like the line point postulate and the 2-point postulate. It's very similar to those 2. So if you have a plane, then there are at least 3 points in it. All right. So if that were to not be true, you would have a plane with less than 3 points, right? So we'd have a plane of some sort with maybe only points A and B in it. So it would be a plane with less than 3 points. All right, we're almost done with our postulates. All right, next one is the plane line postulate. If 2 points lie in a plane, then the line containing them lies in the plane too. So that means that if I've got a plane here, and there's 2 points in the plane, so if this is the case, then if I draw the line between those 2 points, that line is also inside the plane completely. So this line is also laying down in the plane. All right. So if that were not true, you would have a plane with 2 points in it, but somehow the line containing those 2 points would not be in the plane. So the way that would have to look is something like this, where you've got like a line that curves around and somehow pokes through the plane. But as we know, lines are straight, so lines don't do that. Okay. And then we have one more. I'll let people finish drawing here real quick. Okay. So the next one, the plane intersection postulate. So this is another formalization of something we already know. If 2 planes intersect, then their intersection is a line. We know that 2 planes always intersect at a line. And we had a couple different pictures that we drew for this sort of a thing. One of our pictures was something that looked kind of like this. Where we had 2 planes that were intersecting. Maybe this is plane P and plane Q. And where they intersect is line L. It's kind of like that hinge point. That spot where they intersect with one another. Or if we were thinking about that picture that we often went with cubes, where, you know, each face was a plane, and the spot where 2 of the planes intersect, 2 of the faces intersect was like an edge, and that was a line. All right. And so if this postulate were not true, if planes could intersect at something else, that would mean that like 2 planes intersect at a point. So if 2 planes intersect at a point, that would look really weird, right? Like you would have to have planes that kind of curve around and only just barely bump into one another. So we'd have to have something like 2 planes intersecting at a point, which would look something like this. You'd have to have your planes kind of bending around to only barely touch one another at a point. Problem is, planes are flat in Euclidean geometry. And so, if that's the case, if planes are actually flat, they're not going to intersect at just one point. All right. So I know a lot of the what if this were not true pictures are kind of confusing and weird looking, right? The part that we need to understand the most is those first 2 columns. We need to know the postulate itself, what it says, and then a picture of what that looks like, what it means as a picture. So what we need the most is those first 2 columns. The postulate, and then the diagram of what the postulate looks like. Okay. Once you have that, go ahead and turn the page. And we're going to go over some examples of things that we can determine from diagrams and how we want to use these postulates when we look at pictures. So a lot of this today is going to be looking at pictures. So the first couple of problems here say things like, state the postulate illustrated by the diagram. All right. So this first one says, if there are 3 points, A, B, and C, then we've got a line now that's going through those points. All right. So looking through kind of our list of postulates, if you want to flip back to the page that we were on before, we need to find the postulate that involves points and lines. So which postulates involve points and lines? Naya. Yeah, 2-point postulate is one of them. Through any 2 points, there exists exactly one line. What's another? Yeah. And the line point postulate. Yeah, those are the two that we should be looking at when we look at this first problem. The 2-point postulate and the line point postulate. So one says through any 2 points, there exists exactly one line. So if you have 2 points, you can make a line. The line point postulate says that if you've got a line, there's at least 2 points on the line. And this first picture, I don't love just because it has 3 points and then a line. Because really you could support logic for either of those 2 postulates on this picture. You could say that it's the 2-point postulate because you're saying if there are points, then there is a line. But you could also say the line point postulate because you're getting more than 2 points, right? So for this one, since we're starting with points and then going to a line, I would say the 2-point postulate. Although it's confusing because there are not just 2 points in this picture. So I would go 2-point postulate. But typically, if it's the 2-point postulate, there's only going to be 2 points in the picture, not 3. If it was the other way around, then you would say the line point postulate. If there's a line, then there are 3 points on the line. That would be the line point postulate. But anyway. Okay. The next one, we have a plane, and then we have a plane with a line in it. So we need to look for a postulate on our other page that involves planes and lines. The plane line postulate, yeah. It's kind of nice that they're named that way because you can tell from the picture, hey, there's planes and there's lines in this picture. Plane line postulate. So this one is a picture of the plane line postulate. If there is a plane with points in the plane, then the line containing those points is also in the plane. That was what our plane line postulate said. Okay, so that's one style of problem that you guys are going to see. The next style of problem is going to use this picture down here. It says, write an example of each postulate from the diagram. So we want to be able to flip back and forth easily between our diagram here and our postulates. But the 2-point postulate is our first one. And the 2-point postulate said, through any 2 points, there exists exactly one line. So to find an example of it on here, all you have to do is find 2 points that make a line. Yeah. Yep, CH works. Points C and H make the line CH in the picture. You could also use C and D or G and F or anything like that would also work. All right. The next one is the line point postulate, which says that a line contains at least 2 points. So where's a line in that picture that has at least 2 points on it? Yeah. Sure. G and E. So we have line GE that has points G, D, F, and E on it. So if you've got a line that has at least 2, if not more, points on it, you're good to go. That's a good example. Yeah. Yeah, you could say that it's line L and then just list off of all of the points. That also works. Yep. Or you could have said line CH and have C, D, and H on it. That's, yeah, at least 2 points. All right, the next one, the line intersection postulate, which said that we have 2 lines intersecting, then their intersection's exactly 1 point. Olivia. Perfect. Yeah, we've got 2 lines intersecting here. We have line CH and line L, or you can call it line GE if you wanted to, intersect at point D. Perfect. I would write it just so that we get like kind of, I guess, more of where we're going with this. Yeah. The word after which one? Line L. Intersect. Sorry. Yeah. All right. Next one, the 3-point postulate, which said through any 3 non-collinear points, there exists exactly 1 plane. Any ideas where we see that? Yeah.
So like 3 points that are not on the same line.
Exactly. That's what we're looking for here. Basically any 3 points that aren't on the same line. So yeah, Olivia, what do you think? A, H, and G. Yep, that works. Now you see another? GHA. Sure, you can call it pretty much anything that you want to, as long as there are 3 points that are not all on the same line. So you could say points G, H, and A make plane M, since we got that M up in the corner defining the plane. You could say G, B, and D, or C, D, and F. Basically, any 3 points that are not all on the same line will work here. Yep, plane M is what they define. All right. Then we had the plane point postulate. Yeah.
So one is G, D, and B work?
Yep.
And it doesn't matter that G and D are on the same line, right?
Nope. 2 of them can be on the same line, but just not all 3.
Okay.
Yeah, Naya. We are. Let's see. Oh, yeah, that works. So the plane point postulate is that a plane contains at least 3 non-collinear points. So basically, if you look at plane M and list at least 3 points that are not all on the same line, you're good to go. So we can say like plane M has points H, A, D. You could continue listing if you wanted to, B, G, etc. Because it has lots of non-collinear points, and if you list at least 3, you're good to go. So it's kind of like the other way around of the point, of the 3-point postulate. All right, and then the last one that goes with this picture is the plane line postulate, which was the whole, if 2 points are in a plane, then the whole line containing them is also in the plane. So what's one spot that we see that? Yeah. So plane line postulate was, actually it was illustrated up here. If you've got 2 points that are in a plane, then the whole line containing them is also in the plane. Sure, D and G would work, or C and H, or anything like that would work. So D and G are in plane M, and line DG is also in the plane. So D and G are in plane M, and line DG is also in plane M. Okay. The next type of problem that we're going to look at is looks like 9 and 10, where we're going to sketch some pictures of things happening. But we'll wait a minute, let everyone finish writing this one.
What time is the class at?
I believe it's at 10. Or no, it might not be. Let's see. It is BLC 9:55. So we still got like 15 minutes. Okay. Number 9. Sketch a diagram of RS, and this is.
Please excuse this interruption. This is a reminder, if you're in the YES program, please report to the bus zone at this time. YES program to the bus zone.
All right. Number 9, sketch a diagram, and this is supposed to be ray RS. I know it's kind of hard to read. Bisecting segment KL at point R. Question. Yeah, so it would be like if we had a segment KL. And then in the middle, because it's bisecting, right, we would have a point S. Or wait, sorry, a point R. Just kidding. Yeah, and then S looking like that because it's ray RS instead of SR. And then if it's bisecting, we want to make sure we put the little markings on it that show that these two segments are congruent to each other. Yeah, so it's bisecting segment KL. So R is cutting it in half. And we have RS, the ray. All right. And then for number 10, we want to sketch a diagram of segment AB in plane U. Or wait, no, is it segment or line? Just kidding. It's, yeah, these are supposed to be line symbols, which is kind of hard to see because they're written so tiny. All right, so sketch a diagram of AB in plane U. Let's start with that. Let's make plane U. And we're going to draw a line AB in it. And then it's intersecting line CD at point E, and point C is not on plane U. All right, we got a lot going on there. So it's going to intersect at some point E.
And then C's on the outside of like going through.
Right, exactly. C is going to be on the outside of the plane because line CD is going to be poking through the plane at point E. So if you kind of make a dashed line there, you can put point C down here. And then we also have to have point D on the line somewhere because it is line CD. But yeah, so there's a lot going on in that picture. But if you kind of break it up into small pieces, we can kind of see what might be going on. So we start with AB in plane U, and then making sure that point C is outside the plane and stuff like that, and intersecting with the line AB at point E. All right, so that's another kind of problem that we might see. The last kind is a super important kind. Determine what you can assume from the diagram. So we're going to look at this diagram and notice a few things. First, we notice we've got plane L is this top plane here. Plane K is this bottom plane. We might notice that they're intersecting at this line right here. We also need to notice that this is a right angle drawn into the picture. That means that's a 90-degree angle right there. And then we've also got this line that's kind of poking through the plane. Okay, so some things that are important to notice. And basically, these are yes or no questions. So the first one, planes L and K intersect at line PS. What do we think? Thumbs up if that's true, thumbs down if we can't assume that. Yeah, I would say that's true. Because, yeah, we see plane L and we see plane K, and they're intersecting at PS. So we'd say yes. I can get that from the diagram. The next one says points U, M, and O are coplanar. So here's U on plane L. We have O, and then we have M that's supposed to be somewhere like behind the plane here. So thumbs up if yes, they are coplanar. If they're all on the same plane, thumbs down if we think they're not on the same plane. Yeah, I'm seeing a lot of thumbs down on this one. Yeah, I would agree with you. U, M, and O are not coplanar. We can't assume that they are from the picture because M is kind of behind the plane. Which I also don't love that question because really they should have tossed a fourth point in there because technically any 3 points are coplanar. But whatever. We're saying, no, we can't assume that from the diagram because the way it's drawn in the picture, it cannot be assumed. All right, angle QOP is a right angle. Well, here's QOP right there. What do we think? Thumbs up if that's a right angle. Do we have a right angle marking in the picture there? Thumbs down if we don't have a right angle marking for that. Good. Seeing lots of thumbs up for that one. That one is true. Yes, we can assume that QOP is a right angle because we have a right angle marking there. If there's not a right angle marking for it, you can't just assume it. But since there is, we can. Next one. MQ is in plane L. Well, here's MQ. It looks like it's kind of poking through. What do we think? Thumbs up if it's in the plane, thumbs down if it's not in the plane. Yeah, also seeing lots of thumbs down there. Awesome. Yeah, you're right. That one is not something we can assume from the picture. And then lastly, PS and MQ intersect at point O. Thumbs up if we see that, thumbs down if we don't see that. Yeah, seeing lots of thumbs up there. Yes. PS is right here. MQ is right here. We see them intersecting at point O. Awesome. Then we can turn the page. Okay. We do have one more that's kind of like that same style. Which of the following statements cannot be assumed from the figure? So here we go. Points A, B, and C are collinear. So here's A, B, and C. Are they all along a straight line together? No, because A, B, and C are on a bent line. They're not all on the same line. So this would be one that we cannot assume. How about point E is the midpoint of BD? Here's point E. And here's BD. Is E in the exact middle of this line? It is not. So we cannot assume that one either. All right. C involves a bit of a new symbol that we have not seen yet. This symbol means perpendicular, which we will get into more later. And perpendicular means that they meet at 90 degrees or at right angles. Okay. So AC is this line here. BD was this line here. Do they make a right angle where they intersect? Do we see a right angle going on?
Yeah.
Yeah, we got this one right here. Where these two cross each other, there is a right angle. So this is where we say yes. And you won't typically see too many like this just yet because we haven't talked about perpendicular very much. but one to be aware of. We will talk about it more later. And then lastly, AD is equal to CD. Well, here's AD, and it has 2 tick marks on the side. Here's CD, which also has 2 tick marks. So what do we think? Are those equal?
Yes.
Yes. So the only 2 that we cannot assume would be those 2. All right. So that's our notes for today. Go ahead and turn the page once you've got that. And we're going to actually turn to practice B because guess what? All the ones that we just did were practice A. It was just broken out into a different format. So instead, for your guys' assignment for tonight, you guys are going to work on practice B. Let's see. So you're going to do 1 through 6, 7 and 8, 9 through 12, not 13, think about 14, and we'll go not 15 or 16. So 1 through 12 and 14 are your assignment for tonight. And so you guys have the next 5 or 6 minutes. Go ahead and get started on this. Try to get as many as you can done. And then ask questions if you have questions.